Any questions from anything we've covered so far? Okay. Now, let me just go over end of the term type stuff again. First, have you done student course evaluations? Okay, a couple of you have. Please do those, folks. That's very valuable to me. I wish the others were here. I wish I'd have remembered to say it before we lost the two that we've lost already. But please do student course evaluations, okay? I think they'll have it open through at least the end of finals, but I don't know how much after that. So please do them. I know when I was an undergraduate student, once that term was over with, I took that last final. It was like a Etch-a-Sketch. Shook the board and the slate was clean. I never thought about it again. So please do them rather than forget about them, okay? Now, we have class today. This is the day you've been dreading all term, the last day of class, but get over it. And
what about Thursday?
Say again?
What about Thursday?
What about Thursday?
You said this was the last day, but
this is the last day of class. Tomorrow, Tuesday, Wednesday, and Thursday are when you turn in your finals. If you have a final in another class, you may have it on a Thursday, but this class doesn't even meet on Thursday. So you can turn your final in anytime between now and Thursday. Okay, let me give you my hours where I'll be when you can catch me. I'm here. I have another class starting at 11, but it ends at 1:40. I'll be here from 2 until 6 down in my office. I'm up here until then and down there 2 to 6. Okay? That's today. Tomorrow, my first two classes do not meet, so I'll be in my office from 7:45 approximately until 12 o'clock. At 12 o'clock, I have a final in this room, and I'll be up here probably, I'm going to say from 12 to 2. I don't think it'll take them that long, but if they need it, they've got at least 2 hours to do the final. And then after that, 2 to 3:30, I'll be back in my office, 265, and then I'll leave at 3:30 to go over to the Birmingham East Campus, Ethel Hall, Health Professions Building in room 103. When you come in the door, there's a angle like that. Take the left angle, go right past the restrooms. The first door on the left is 103, room 103. I'm in there receiving the finals from that physics class. Okay?
What time you said that was?
Say again?
What time?
From 4 to 6 on Tuesday and Thursday. Okay, if that's more convenient for you, you can turn them in there. A couple students from my other class brought finals by last Thursday. Okay, Wednesday, I'm here on this campus, down in my office from 265, from 7:45 in the morning until 6 o'clock in the evening. That's probably the biggest chunk of time. That's when, anytime then you can bring your final then. Okay, Thursday, no more finals, so I'm in my office from 7:45 in the morning until 3:30. At 3:30, I leave to go to the Birmingham East Campus. I'm there from 4 to 6. Okay, it takes me about 30 minutes to get there. So 4 to 6 on Thursday. I've got to have everything in by then because the next Monday, the college is not open that Friday. I wouldn't be here if it was, but it's not open on Friday. And I will be on campus Monday, but we've got to have grades in by noon on Monday. So I can't you can turn it in, but you'll be getting an incomplete for the course until I can get it graded and get the grade changed. I'll try to do that as soon as I can, but anything that comes in Monday morning, the odds are that I'll be able to grade it and get the grades entered and all like that very slim, because the grades have to be in by noon on Monday. Okay? So, but I'll be here all day that day from 7:45 in the morning until 6 o'clock that evening. All right, any questions?
What time tomorrow? On the Birmingham?
Tomorrow on the Birmingham campus, 4 to 6.
Okay.
Same on Thursday.
Okay.
Okay. All right. Then let's continue. And we were on page 283 with Chapter 4, Integration, 4.4, Fundamental Theorem of Calculus. We had done the first two parts of this exercise, example, but we had not, goodness gracious, my pen is all wound up. Okay. We had not done the C part, is my memory. Is that where y'all were? Hadn't we done this one? Y'all remember? My mark is that we were on C. Anybody? Is that right?
We finished B, but we were doing C.
What's that?
We did A and B, we didn't do C.
Okay, that's what I was thinking. So here's C. Okay, that's yes in Spanish. Okay, C. Okay. So, how, and they've already done the first part for us. That really irritates me. Let me go back one. Let's us do C. Let me get my pen set up. So sorry we're late getting started. Here is C. We're integrating from 0 to pi fourths secant squared x dx. Okay? Now, first, when you have a problem like this, you better make sure the problem makes sense. Okay? Now, what do I mean by that? Well, here's one thing. Notice your limits here, from 0 to pi fourths. You better make sure that secant is defined from 0 to pi fourths. Because if secant is, and secant is a discontinuous function, and if it's discontinuous in that range, you can't do the problem. So don't even try, okay? So you first ask yourself, is secant defined from 0 to pi fourths continuously? Here's where you have to think back, oh man, that hurts, to your trig days. And what was secant? What does it look like? Does anyone remember? Secant and cosecant look basically like this. Okay? Remember, sine and cosine always stay between plus and minus 1, right? And secant and cosecant, since they're the reciprocals of that, they're always outside of plus or minus 1. So I'm going to put my plus 1 here, my minus 1 there. Now, cosine is the inverse, the reciprocal of secant, right? So cosine starts at 1 and goes down to 0 at pi halves, right? And came from 0 at minus pi halves. That's enough to tell you right there. Secant is not defined at minus pi halves, nor at plus pi halves, or at any half pi. Secant is not defined because cosine is 0 at the half pi's. So therefore, secant does something like this. Yeah, so between 0 and pi fourths, here's 0, pi fourths is here, secant is definitely defined there. So yes, we can do the integral. You always should think of that before you start blindly wailing away at it. Okay, now that we know we can do that, the question is, what is the antiderivative of secant x? Secant squared x. Anyone know? In other words, is there a function that when you take its derivative, you get secant squared? I wonder who your Cal 1 teacher was. Oh, that was me. Tangent, exactly. That is tangent x. And tangent x we're going to evaluate between 0 and pi fourths. Okay? So, how do we do that? You help me. Help me, help me. Anybody? What is the tangent of pi fourths? Minus the tangent of 0. This is the fundamental theorem of calculus. What is tangent of pi fourths? Say again? 1, exactly. What's tangent of 0? 0. So the answer is 1. All right. Good deal. Kind of like pulling teeth, but I'm not a dentist. Okay. So they did, and for some reason they went on and showed you what it was. The antiderivative of secant squared is tangent x. Evaluate that from 0 to pi fourths. That would be tangent, and that would be 1 minus 0 is equal to 1. Good deal. I would have written out one more step there. I I think I could handle 1 minus 0 being 1. It's the one before that, tangent pi force minus tangent 0. That's the one that needed to be written. Okay, any questions on that? Pretty straightforward, right? All right, they're skipping examples 2, 3, 2 and 3. So let's go back and do those. Sorry. Oh, okay. We'll start here. All right. Evaluate this. The integral from 0 to 2, oh boy, what a pain in the neck this is. Absolute value of 2x, oh, that's not too bad, minus 1 dx. Okay? Can anyone tell me or remind me what in the world the absolute value function means? Say again?
What you said?
What the absolute value function is.
Oh, it just means it's never negative.
Okay, the answer to that is never negative. Okay? That gives me what the answer is, but how is it defined? How is the absolute value function defined? Anyone recall that?
Everywhere above,
What's that?
like all the y values are positive.
Okay. All right. And here's I think how you're saying that. I hope it is anyway. Here's how we define this. I'm going to write it up here. The absolute value of 2x minus 1 is defined as a piecewise defined function, and it is 2x. Okay. I guess the first thing we need to do is determine where the point is, basically. Okay? Where is that 2x minus 1 equals 0? Let's do that first. 2x minus 1 equals 0. Where is that equal to 0? You can solve that equation if you want to. It's pretty easy. At 1/2. Add 1 to both sides, and that gives you 2x is equal to 1, and divide by 2, and you get x is equal to 1/2. So this is, and by the way, as long as x is greater than 1/2, you've got a positive value. So it's 2x minus 1 anytime x is greater than or equal to 1/2. Therefore, it's negative 2x minus 1 anytime x is less than 1/2. That's how you do an absolute value function. That's how it's defined. Find the 0 of it, the point of it. Over here is the minus of that. Over here is just that value. Okay? So, from 0 to 2, we're part of the time in the lower part, and the rest of the time in the upper part, right? You see, this is x going from 0 to 2. Well, from 0 to 1/2, you're in the lower part there, and from 1/2 to 2, you're in the upper part. Does that make sense? This is really kind of strange for them to give this kind of a, it's not that difficult, but this sort of complicated issue here when they're just teaching you how to do this, okay? So, what we've got to do is split this into two integrals. The first will be 0 to 2, and then we'll be evaluating this minus thing, okay? I'm sorry, 0 to 1/2. Sorry. Well, I didn't need to do that. 0 to 1/2, we'll evaluate, and I'm just going to flip them around, 1 minus 2x, okay, dx. Does that make sense? I'm doing the opposite of this, the negative of this, from 0 to 1/2. Because anytime x is less than 1/2, you use that form. So rather than having a negative in front, I just distributed the negative across with a positive in front. Is that okay? Okay. Then we will do the second part, which is the integral from 1/2 to 2, and then we'll use the upper definition, 2x minus 1 dx. Okay? All right. Can you do the antiderivative of 1? Anybody? Second?
Is it just one? I'm not sure what the antiderivative is.
Okay. X, exactly. Because when you take the derivative of x, you get 1. So the antiderivative of 1 would be x. It undoes it. That'd be x minus, what's the antiderivative of 2x? X squared. Okay? And we'll evaluate that from 0 to 1/2. Okay? Plus, this is not that much more difficult, but what is the antiderivative of 2x? X squared, 1, second, x, and we'll evaluate that from 0 to 2. I'm sorry, 1/2 to 2. Trying to make up for lost time here by going too fast. And all right. So that's what our evaluation is going to be. On this first one, you do the substitution. Tell me what you get. Anybody? Anybody? Help me, somebody. 1/2 minus. No, okay. Let's only do the x squared. 1/2 squared. 1 what? 1/2 squared is not 1. 1/2 squared is 1/4. Okay. I'll do the 0 part because I'm able to handle that. 0 minus 0. Okay, I did that one. Okay. So that's the first part. Plus, now you do the second part here. Help me. Anybody? Anybody? A little louder? Okay, let's start with the upper part. 4 minus 2 minus, now we do the minus with the 1/2 in there, and what does that give us? I think someone said it earlier. 1/4. Second?
1/4.
Minus
1/2.
1/2. Okay. Now, watch your signs and watch your subtractions here. 1/2 minus 1/4 is what? 1, say again? 1/2 minus 1/4.
Oh, it's just 1/4.
1/4 plus 4 minus 2 is
2.
2 minus, and what's 1/4 minus 1/2?
Negative 1/4.
Negative 1/4. Okay? And this will be a 1/4 plus 2 plus 1/4. And that would be
2
2 and 1/2. Very good. Okay? Let's see what they got. 5/2. That's the same answer. Okay? 5/2. Very good. Any questions on that? That's rather bizarre for them to jump into a piecewise defined function when you're just getting your feet wet doing fundamental theorem of calculus part 1. Okay. So, all right, to erase this and go to example 3. Yay or nay? Okay. Example 3. Find the area of the region bounded by the graph of y is equal to 2x squared minus 3x plus 2. Okay? That's the first part. The x-axis. Okay, that's the second part. And the vertical lines, x equals 0 and x equal 2. Okay, now they say shown in the figure, but of course they don't show us the figure. So I'm going to try to reproduce as quickly as possible, which is not very quick, this. So we'll do a 1, 2, and it's going to be something, 1, 2, starting here, going down to here, and nope, I don't quite have it right. It goes down to here and up to somewhere up here. Okay? Okay. It's something like that. It's a parabola. And we're looking for this area under here. The parabola here, which is 2x squared minus 3x plus 2. The x-axis down here, x equals 0 here, and x equals 2 over there. All right. You want to try to figure that out on your own or use calculus? Please say use calculus. Okay. How do we use calculus to do that? No, we don't. No. If you're finding the slope of a tangent line, you take a derivative. Finding area under a curve, you say again? Antiderivative or integrate. Okay? And that's what I started to draw here until I heard the answer. Okay? You integrate. That's what you're doing. You're summing. Oh, that hurts. Okay. You're summing, you're breaking this into little strips here, right? Your dx is the width of the strip. Your f of x is the height of the strip. There's your f of x, that's the y value. And you're integrating from 0 to 2, right? You're summing those up. That's an integral, okay? Derivative is, and that was a good answer early in the class, but now it's integrate, okay? All right, I'm back. Okay, so like I just said, you're integrating from 0 to 2 of 2x squared minus 3x plus 2 dx. There's your height of the strip, there's your width of the strip, and you're summing them up or integrating. So what's the antiderivative, to use Tyler's term, of 2x squared? Help me, somebody. Antiderivative of 2x squared. A little louder. Okay, it's going to have an x cubed in it for sure. The 2's going to be there.
Over 3.
Over 3, got it. There's the first part. Next part.
Negative 3x squared over 2.
Over 2. Is that what you said?
Yeah.
Okay, I thought so. Okay.
Plus 2x.
Plus 2x. Evaluate that between
2 and 0.
Yeah, only we usually say 0 and 2. Okay. Next. Second. You should. Now is where you plug in. You plug in the upper value first, and then subtract from it to plug in lower value. Right? Fundamental theorem of calculus part 1. Okay? So that gives you, help me? A little louder? Did I hear a 16 thirds? Minus
12 over 2.
12 over 2, which is
6.
6.
Plus 4.
Plus 4. I'll do the 0 part. Minus 0. Okay? Y'all okay with that? You don't mind me jumping in there, do you? Okay. Those are all zeros. And what does that give us? Well, this part here is a minus 2. So let's make that minus 6 thirds. So that is 16 thirds minus 6 thirds. And that's equal to what? Not that hard. Help me, somebody. 10/3. All right. Let's see what they got. Yes, they got 10/3. All right. Let's move on then to the mean value theorem for integrals. All right. Okay, sorry about this. All right, mean value theorem for integrals. We saw that the area of a region under a curve is greater than the area of the inscribed rectangle and less than the area of the circumscribed rectangle. Okay? What are we talking about here? Okay. If this is a curve, okay, and you break that into an inscribed rectangle and a circumscribed rectangle. The inscribed rectangle would be from the minimum point here across to there. That would be the inscribed rectangle. The superscribed rectangle would be from the maximum point down. They didn't show those two, but those are your two. So the areas in between the two. The mean value theorem for integrals states that somewhere between the inscribed and circumscribed rectangles, there is a rectangle whose area is precisely the same as that under the curve. Okay? In other words, looking at their picture here, the area you overestimate here is exactly equal to the area the rectangle overestimates here than what the rectangle underestimates there. So there is a rectangle that fits that has the same area, precisely the same area. Definitely not the same shape, but the same area. Okay? Well, what is that area? The rectangle would be, okay, there's some value C in between A and B, such that, and now, here's the requirements here, folks. The function has to be continuous. Has to be continuous, right? If it's not continuous, how can you do this? You can't, okay? So, if it's continuous, there's some value C in between the A and B where the rectangle width times height is exactly the same as the area under the curve, okay? They're a little bit too far this way, and this is smaller than that, okay? This far, this is smaller than that. Somewhere in here, there's a place where this area and that area are exactly the same, and you have your C there, okay? So that's saying f of C, whatever value that is, times your b minus a, is going to be exactly equal to this integral of f of x dx between a and b. That should be minus a again there, okay? That's what the mean value theorem is stating for integrals. Okay? Now, here's how they state it. Mean value theorem for integrals. If f of x is continuous, there is a requirement. It has to be continuous on the closed interval from a to b. Then there has to be some number c in that closed interval a to b such that the integral of f of x dx evaluated between a and b is exactly equal to that f of c, value c, times b minus a. Okay? There is some value there. All right. That's all they do. Okay? They do a little proof on it, and I'll let you read through the proof and work through that. We just don't have time to do that now. Let's move on to average value of a function. They don't give an example. The example is going to follow this. Now, if you think back at what that's saying, there is a sense then, because f of c obviously is between f of a, which would have been down here, and f of b, which is up there, there's some sense that f of c may be the average value of that function on that interval. Okay? And that's what this is going to be talking about here. The value of f of c given by the mean value theorem in the mean value theorem for integrals is called the average value of f on the interval from a to b. So the definition of that is if f is integrable, okay. Remember last time they said f is continuous. But if you remember, if f is continuous, it is therefore integrable. Okay? No, maybe not. I think it probably is. Yeah, it should be integrable. But if f is integrable on the closed interval from a to b, then the average value of f on that interval is the f of c that we had here times b minus a. Let's just divide both sides by b minus a. It's 1 over b minus a times the integral from a to b of f of x dx. That's it. Just evaluate this integral, definite integral, evaluate that, then divide by the length, and that gives you your f of c. Okay, the average value. In this figure, the area under the region under the graph of f is equal to the area of the rectangle whose height is the average value. So this one's a lot harder to see. You just have to take their word for it. Here you're going from a to b. Here your f is here, and f of a is here, f of b is here. Now, remember, I'm surprised they haven't thrown this in there too. Remember, f almost always has to be greater than or equal to 0, right? Because if you have portions down here, the area isn't making as much sense, okay? They haven't said that, but it's still true, okay? Yes, that's what, part of what they mean integral. I don't know. Okay, so the area under this curve, that's going to be the pink and the purple areas together, okay? That's the area under the curve. They're saying that's exactly equal to this rectangle here. There's your f of c somewhere. Actually, there's 3 places that you could do a c. F of c there, f of c there, or f of c there. It doesn't matter which c you choose. There's some c in between a and b such that f of c times b minus a, that area is the same as the area under the curve. So therefore, that value, f of c, whichever one you choose is here, that's going to be your average value. How do you calculate it? If you can do the integral, integrate that, and then divide by the difference between b and a. Okay. To see why the average value of f is defined this way, partition AB into n subintervals of equal width. It's like we're going backwards here. Riemann sums. Delta x is b minus a over n. If c sub I is any point in the ith subinterval, then the arithmetic average, or the mean of the function values at the c sub i's is, boy, I really, they're using a for average. Before they used a for a sub n as the coefficient of a polynomial. That's not this, okay? This is just the average over n subintervals. Yeah, n subintervals is 1 over n, okay? You got n of these things, f of ci plus 1 plus f of c2 plus f of c3, all the way up to f of cn. You're taking the average of those and then dividing by the number you had, n. So that's the average, and that's what this is. So this is how that is defined when you're using some sort of c in the middle, not necessarily the same c as we were talking about before. And by writing the sum using the summation notation, and then multiplying and dividing by b minus a, which is a weird kind of way to think of it. So this is a sub n is 1 over n, that's outside the notation. the summation from I is equal to 1 to n of f of ci, and you do this, multiply and divide by 1 over b minus a over n. Now, that looks a little bizarre, but let's swap. And the b minus a has nothing to do with your counter at all. So it doesn't have to be inside the summation. In fact, it really isn't, but let's put this b minus a over here and this n over here. Well, what is that? This is your delta x. Remember? Delta x is b minus a over n. So it's 1 over 1 divided by b minus a times the sum of f of c sub I dx. And if you let the n goes to infinity, this is the integral f of x dx. And there you have exactly what we're looking for. Finally, taking the limit as n goes to infinity produces the average value of f on the interval as given by the definition. It says in this figure, notice that the area of the region under the graph of f is equal to the area of the rectangle whose height is the average value. Okay? Say that. You can't look at that and see it, but they're saying that is the case. All right, let's do example 4, bottom of page 285. I'm all set now, I hope. All right. I'm not as bad as it looks. Yes. Okay, let me get it. Okay. Here we go.
Thank you.
All right. All right. Please do the pseudo-course evaluation. All right. Is this a good time for a break? Okay. Let's pause just for a moment here, because I think I could use one now. Sat down. Any questions from what we've done so far? All right. And example 4 says, find the average value of f of x is equal to 3x squared minus 2x on the interval from 1 to 4. Okay? Just because of the definitions and stuff, it's probably a pretty good idea to make sure this question makes sense. So in the first place, can we find an average value of a function like that? What's the requirement of the function? Actually, can say it either of two ways. Either function needs to be continuous or integrable. How about this one? Everywhere. That's a polynomial function. Polynomial functions are continuous everywhere, integrable everywhere, especially on that interval, including the interval from 1 to 4. So, how are we going to find the average value of that? Help me help. Take an integral, okay? Remember, we're in the... Say again?
Wait. I did the slide before this. Was the slide before this not about the mean value theorem?
It was related to the mean value theorem. It was the average value.
Okay. Sorry.
Okay? But it's related to the mean value theorem. Okay? So, how do we do this? Okay, yeah, we integrate it. All right? So the average value, and they were calling it little a. I really don't like that, but let's see. They don't even name it. So let's call it just the average value of the function. Okay? Is equal to what? And you said integrate. I agree with that. How would I fill that in the integral? Help me. What am I integrating? From 1 to 4 of? Say again? 3x squared minus 2x. Anytime you have an integral, you better have a dx. Okay? Now, there's one other thing to get that. This will give you the integral of that. What we want is the average value. That's not the same thing. So what's the average value? Hint, you divide by something.
B minus A.
B minus A, the length of the interval. Okay, and what's your B and what's your A here?
4.
4 is the B.
4.
Say again.
4.
4 is B. What's your A?
2A. So
What? I'm sorry?
Isn't it 2A?
No.
1.
1. This is the interval from A to B. There's 1 to 4. So B is 4 and A is 1. 4 minus 1. Okay? And what's the antiderivative of 3x squared?
3x cubed over 3.
Okay, which is? Three x cubed over 3?
Yeah.
3 over 3 is? 1. So it's just x cubed, right? Okay? Minus. Help me.
2x squared over 2.
Which is?
X squared.
Say again?
X squared.
X squared. Evaluate that between?
4 and 1.
Okay. I usually say 1 to 4. Okay. So this will be, what is 1? 4 minus 1? 3. All right. Pretty exciting, isn't it? Okay. And next?
4 cubed.
Which is?
It's going to be 64.
64 minus
16.
16.
Which is 48.
Say again?
Which is 48.
Where you get a 48? Oh, you're subtracting. Okay, let's go on and do the rest of it.
Oh, my bad.
No, it's okay. Minus 0. It's 1 minus 1. Happens to be 0. It's not always 0, but this time it happens to be. Okay? So this will be 1/3 of, as you said, 48. And what's 1/3 of 48?
That's going to be 16.
16. You got it. So the average value is 16. Lots of 16s in there, but they weren't really related to one another.
You leave it up just for a little bit.
Say again? I'll leave, yeah. As long as you need. Okay? The next slide will show the same type stuff, I think. It's better. All right, so let's see how they did it. The average value is 1 over b minus a times the integral from a to b of f of x dx, which in this case, our a is 1, our b is 4, so this will be 1 over 4 minus 1 times the integral from 1 to 4 of your function, which is 3x squared minus 2x dx. Okay? Fraction's easy, that's 1/3. And the antiderivative is easy, x cubed minus x to the squared. Evaluate that between 4 and 1, and that would be 1/3 of 64 minus 16. That was 4 squared minus 4 cubed minus 4 squared, minus 1 cubed minus 1 squared is 1 minus 1 happens to be 0. So that would be 1/3 of 48, which is 16. And there's the description of it for you. At 1, your function is equal to 1, and 4 is equal to 40 up there, okay? And you're integrating this from the area under here and finding the rectangle whose area is the same thing, and that would make this the average value is right at 16. Okay. The C sub I is not really all that important. Can't think of any place where you need to know that, but you what's more important is the average value. All right, any questions? Need this any longer?
No.
All right, then let's move. Let's back up one because they do not show example 5 either. So let's do example 5. At different altitudes in the Earth's atmosphere, sound travels at different speeds. Anyone have an idea why that might be the case? At different altitudes in the Earth's atmosphere, sound travels at different speeds.
Because the compression of air, like the air molecules in the air are more densely compact as you
Near
get
the
closer to
surface.
the-
That's
near the
exactly
surface.
right. Your air molecules are denser, closer to the Earth because the weight of the air molecules above them. The higher you go, the less weight above them, so they're less densely packed. So that affects the speed of sound. Also, other things that affect are temperature, and of course, as you go up, typically the temperature is going down as well. So there's several things. Okay, at different altitudes in the Earth's atmosphere, sound travels at different speeds. Speed of sound S of x in meters per second can be modeled by, this is a model, it may not be exact, but here's the model. S of x is equal to piecewise defined function, if I've ever seen one, minus 4x plus 341. That's for 0 less than or equal to x is less than or equal to 11.5 meters high. Now that's really not all that high, okay? That would be about 11 yards off the ground, 12, 15 yards off the ground. So it's not that huge. Okay, 295, a constant from 11.5 to 22 meters off the ground. That's about 25 yards up. 3/4, I can't read. 3/4 x plus 278.5. What a nice round number. That's from anywhere between 22 and 32 meters above the ground. Okay, this is rather bizarre. I've never seen this one before. 3/2 x plus 254.5. That's anywhere between 32 and 50 meters above the ground. That's half a football field, or a little bit more, maybe counting the end zone sticking up into the air. And finally, negative 3/2 x, which is rather strange, plus 4.04. 404. I don't know where I got the point from. Okay. Okay, and that's anywhere between 50 and 80, I'm sorry, I can't read, meters above the ground. So that's almost a football field up, which isn't really all that far up, okay? Now, oh no, I'm sorry, wrong. They said the speed of sound measured in meters per second, but then these x's are measured in kilometers. That makes a lot more sense. Not football fields, we're talking about kilometers. X is the altitude in kilometers. above the ground. What is the average speed of sound over the interval 0 to 80? Okay. Now they draw the graph for you. I really would rather not. If you have books, hopefully you can see that graph. Basically, what we've got to do is a piecewise integration. Okay? These are continuous functions, and they show you here it is a continuous function. Okay? Speed of sound is on the horizontal axis, vertical axis, altitude in kilometers on the horizontal axis. Okay? So this is making more sense than it originally did to me when I was reading it. I thought this really isn't making a lot of sense. So when you talk about 80 kilometers up, you're talking about 48 miles up. So that's up there. Okay, so these are much bigger intervals than what I was thinking. I thought this really makes no sense, but it does now with those in kilometers. Okay, so it's sort of strange to have this defined in meters per second. That was it, wasn't it? Meters per second. Yeah, but the x's are in kilometers. But it's okay. I mean, that's how they define it, so that we'll be all right with it. Okay. What's that?
I said, do you do a conversion?
I don't think so, because the formula is set up to go back and forth. Okay, so we'll take their word for it. So what we have to do is integrate piecewise. Okay, so what we're going to do, the integral of this dx is going to be the integral of each of the pieces, and then we're going to have a 1 minus 1 over 80 in front, because that's the b minus a. If you're going from 0, and I think they did, yeah, between 0 and 80. So that's out front, and your first interval will then be a minus 4 x plus 341 dx, okay, and that's from 0 to 11.5, okay, plus the integral of 295. I think we can do that, can't we? That's just 295 times that, well, I'll write it down. 295 dx, okay, and that's from 11.5 to 22. Goodness, my knee's hurting. Okay, plus the integral from 3/4 x plus 278.5. I hope I copied all this right. Dx. Might be helpful to put those in parentheses, maybe not. And that's from 22 to 32, plus the integral from 32 to 50, and that now is 3/2 x plus 254.5, 3/2 x plus 254.5 dx, and then finally you have plus the integral of negative 3/2 x. This will be from 50 to 80, plus 404.5 dx. Okay? Now, none of these are hard integrations. The difficulty or the time, the effort is going to be spent doing the evaluation. Just for instance, what's the antiderivative of negative 4x plus 341? Anybody? Antiderivative of negative 4x plus 341. Okay. Thought it was going to be pretty easy. antiderivative of minus 4x. Say again?
This doesn't sound right. I was gonna say like x to -4 over 30. I know it's gonna be over 30, but I can't remember about the x part.
Okay.
The x part.
Remember, you just bump this up by 1. Just like when you take a derivative, you reduce it by 1. You do an antiderivative, you increase it by 1. So that would become a x squared 2. And then you divide by 2, because you divide by the n plus 1, 2. And 2 will go to the 4 twice. So it'll be minus 2x squared. Right? Okay. That's the first part. What's the second part? Help me. Second. Sorry. Y'all awake yet? Okay. Next. It's not that bad. Antiderivative of 341 dx. Help me, somebody. Plus 341x, exactly. Okay? And you evaluate that between x equals 0 and x equals 11.5. Okay? Next one is really pretty easy. What is it? Say again? I can't hear you.
I said never mind.
Oh. Okay, I won't. 295x. And that's evaluated between 11.5 and 22. Okay? And you keep on going down the line that way. And none of these integrations are very hard. The hard part is just doing the evaluation, because you have to do the upper one minus the lower one. But you can do them. They're not that bad. Okay? And they each give you a value, and you add them all together and then divide the entire amount by 80. And that'll be your average value of the speed of sound in meters per second. Okay? And that gave you something on the order of 308 meters per second. Just seems like a terrible waste of class time to have to do all those calculations. But they're not bad. They're just, you have to do them. And then add them together. And then divide by 80. You get about 308 meters per second. Which is, fairly reasonable. I think they usually use, I don't remember. It's not far off to do 100 and some odd feet per second, and that makes some sense. All right. So do you mind if we just don't go through all the drudgery of all those calculations? You can follow it in the book, see if you get the same answers they got there. Okay? So let's move on to do second fundamental theorem of calculus. Other books will call this fundamental theorem of calculus part 2. Okay? Earlier you saw that the definite integral of f on the interval from a to b was defined using the constant b as the upper limit of integration, x as a variable of integration. Okay? However, a slightly different situation may arise in which the variable x is used as the upper limit of the integration, and to avoid that confusion then of using x in two different ways, t is temporarily used as the variable of integration. And they remind you of this. In a definite integral, remember that the definite integral is not a function of this variable of integration. In fact, quite often that's called the dummy variable. Okay? And there's not a derogatory use of dummy, by the way, but it's just used to represent whatever you have. So the definite integral is a number, because remember, when you put these units in here, you don't wind up with x's anymore, because you're substituting these values in for x's, and you wind up with a number. Okay? So the f of x is a function of x, but when you do the integral, it's not anymore. Okay? Now, that's the definite integral as a number. Here's the definite integral as a function of x. Now you've not got an upper limit, but that's going to be your variable. So when you, remember when we use capital F as the antiderivative of little f, that would be your capital F of x is defined to be the integral from a to x, a variable up here, of f of, you can name this anything you want to. They usually use TDT, you can use SDS, you could use stickman, d-stickman, you can use anything you want to in there, because that doesn't really enter the picture, because what you're going to do once you do the antiderivative of this, you plug x in for the first part minus a in for the second part, and then you wind up with a function of x, not of t or stickman or anything else. Okay, so here is example 6. Let's evaluate this function at 5 different values. It's not going to be that bad, I don't think. I hope not. So, what is the antiderivative of cosine x? Cosine t?
Sin t?
Sine t, is that right?
Yeah.
Yes, okay. Evaluated from 0 to x, right? Agreed? And that would be plug in the x for the first value, and that would be sine x, and plug it in for the second one, and what do you have? Minus sine of 0, and what is sine of 0? Nope. 0. So that's your sine x. Evaluate this at these 5 different values. Sine of 0 is, we already said that, 0. Sine of pi 6. I'm going to talk to your trig teacher. Oh, I was your trig teacher. Okay. What's sine of pi 6?
Isn't it 30 degrees?
Pi 6 is 30 degrees. What is sine of 30 degrees or sine of pi 6? That's what we're looking for. 1/2, exactly. And for pi fourths, sine of pi fourths. Second, square root of 2 over 2. Sine of pi thirds. Square root of 3 over 2. And the sine of pi halves. 1. Got it. Okay? Now, I think I told people in my class before, and I thought I maybe had told this class too, but one sort of easy way to remember this is for the sine only. Okay? And it's for these special values, pi 6, pi 4, pi 30, and pi half, 0 to that. And if you think in terms of degrees, 0, 30, 45, 60, and 90. Okay? Then take a look at this. This is the square root of 0 over 2, which is just 0. Square root of 1 over 2, which is just 1/2. Square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2, which square root of 4 is 2, and 2 over 2 is 1. So that's a real easy way to remember that. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. Just happens to work out that way. And if you had cosines, they just reverse themselves. This would be 0, 1/2, square root of 0 over 2, square root of 3 over 2, 1. All right. So basically what this is saying is you could have done 5 integrations here with each of these in there and gotten these values, or just do one with the x in there and then plug in the values for x. And that's pretty easy to do, okay? Not too awfully bad to do anyway. Yeah, that hurts. All right, let's see how they did it. Hopefully not far off, but maybe with a few more graphics. You could evaluate the 5 different integrals, one for each of the given upper limits. If you're really a hard worker, and some of you are, that's fine and good, definitely a way to do it. Or use the second fundamental theorem of calculus and just evaluate it once and then plug in the different values. And that is what we did. That sine t evaluated from x0 to x. That'd be sine x minus sine 0, which is simply sine x, and then just plug in the values. Okay? Alpha 0 is equal to 0. There's no area under that line. Okay? Alpha pi 6 would be 1/2. Alpha pi fourths would be square root of 2 over 2. Alpha pi thirds would be square root of 3 over 2. And alpha 1/2. All right. Make sense? So it's the area under the curve of cosine t from 0 to x. All right. But, see, this works for values that aren't quite so common, like 15 degrees, pi eighths. You know, you could do any of those just plugging in. All right. So another way to look at that, remember the capital F of x we were calling the antiderivative at one time. You can think of that function f of x as the accumulating the area under the curve of f of t is equal cosine t from t equals 0 to x. For x equals 0, the area is 0 because there's nothing there. There's you're at 0 and you're going to 0. And for x equal pi halves, then you accumulate a little bit more and more and more. Okay, gives the accumulated value of area under the curve of the entire region from 0 to pi halves. This interpretation of an integral is called as a accumulation function, is used often in applications of integration. Yeah, I guess I know what they're talking about there, but I've never used that terminology. But yeah, that's what you're doing. Okay. Sorry, I said that. In example 6, note that the derivative of f is the original integrand, with only the variable changed. That is, derivative of f of x, that's the derivative of sine x is cosine x. That is the derivative of the integral of cosine x dx. Hey, look at this. Here we have an integral, and here we have a derivative. The integral undoes the derivative because the thing in here is the same here and here. Just you replace the x with the t with an x here. And this is an illustration that a derivative undoes an integral, and as we'll see later, an integral undoes a derivative. This result is generalized as the following theorem, which is called the second fundamental theorem of calculus, or in some books, the fundamental theorem of calculus part 2. Okay? If f is a continuous function on some open interval I containing the value a, then for every x in the interval, the d by dx of the integral from a to x, f of t dt, is simply going to be f of x. You just plug this variable here in for the dummy variable there, and you've got d by dx of that. Because when you take a derivative, you don't have a constant left over. That's the only difference. When you integrate last, you're going to wind up with a constant of integration. Okay? But I should jump ahead there. Using the area model for definite integrals, then the approximation f of x dx, delta x, would be the integral from x to x plus delta x of f of t dt. That would just be the function. If here is your delta x here, and you're just doing this estimation of what f of x times delta x is, okay, then this will be the integral, approximately the same as the integral from x to delta x of f of t dt, okay? dt is the same as that, okay? This can be viewed as saying that the area of a rectangle of height f of x and width delta x is approximately equal to the area of the region lying between the graph of f and the x-axis on the interval from x to x plus delta x is shown here. Okay, I don't know why we're reviewing all this, but I guess it's fun to do. So let's do example 7. All right. Evaluate that. d by dx of the integral from 0 to x of square root of t squared plus 1 dt. Oh man, that's an integral we haven't done before, isn't it? That's really difficult. I think you're going to have to use a table for that. But not really. You're not looking for the integral of that. You're looking for the derivative of the integral for that. And what does this tell you it is? Fundamental Theorem of Calculus Part 2, or Second Fundamental Theorem of Calculus. This thing undoes that thing, leaving you what? Second, the square root of, second, x squared plus 1. That's it. All you do is plug in the variable at the top there, x, into your integrand, because your integral is undone by your derivative, so you're left with just the integrand. Just like an inverse function, this is an inverse operation. Okay? And unfortunately, that's all there is to it. There's not much else. So I'm going to, any questions? Show you how they did it. Note that f of t equals square root of t squared plus 1 is a continuous function on the entire real number line. Yeah, because t squared is always positive. Add 1 to it, it's always positive, so that'll be good everywhere. So you can certainly do it between 0 and x. And so using second fundamental theorem of calculus, you can write d by dx of the integral of 0 to x of square root of x t squared plus 1 dt would just be simply square root of x squared plus 1. Done. That's all you have to do. If you take a derivative of an integral, that's all you have to do. Use what's inside. Let's see. That was example 7. By the way, they did have a proof of the second fundamental theorem of calculus. Oh, we sort of walked through that, so never mind. Before we get to net change theorem, there is one more example, that's example 8. So let's go back and do example 8. All right. Find the derivative of capital F of x, where capital F of x is the integral. Whoa, a little bit different here, and of course this would not be one that we would show you on the slides, because this is more difficult. Pi halves 2x cubed cosine t dt. Okay, they're looking for the derivative of this. So we're looking for f, capital F prime. Now written, okay, now that's not the best way to write this. Okay, given the f, we're looking for f prime. Given the f, what we're looking for is f prime of x. of course, f prime of x is df dx, right? Okay, so df dx, but the f is this function here, so this would be d by dx of the integral of pi halves to x cubed cosine t dt. Okay? Now, Houston, we have some issues here. Okay. Do the integral, the derivative of the integral takes what's up here and plugs it in there. Okay? But that's not f of x. That's capital F. Oh, let's see. Yeah. That's just cosine of. It hurts. I think that's just cosine of x cubed. Okay? Except, I knew there was some issue here when they did it as a chain rule. Okay? So let's back off and do what they did. Okay. Should have followed along with them, but I was going to try to do it a slightly different way, but it just gets more confusing that way. Okay. Because this isn't an x, it's an x cubed, right? We want it to be a single variable. So let's make it a single variable. Let's let u equal x cubed. Now this is called the substitution, and we haven't quite done that yet, and I'd hoped to get to do that today. I don't think we're going to have a chance to, but let's get as far as we can. If you do that, then du is equal to what? If u is equal to x cubed, what is du equal to?
X cubed.
Say again?
You said like u equals x cubed, that means dx. No, du is equal to dx cubed, right? Or,
No. If u is x cubed, then take the derivative of u. What would that be?
oh, taking the derivative.
That's what d stands for, right? Okay.
That's going to be 3x cubed plus the square.
3x squared dx. That's written in differential form. Okay? Which, another way you could say, or du dx is equal to 3x squared. So whichever way you're going to find most useful. Okay? So if we put that in, then we have and they take you through this, and when they're doing it, it's not exactly clear why until you get to the end and they say, oh, that's why they did it. So that's why I didn't want to do this way, but it's basically about the only way you can do it. Well, it's not the only way, but it may make the most sense. So let's see. What we're ultimately going to look for is df, or f prime. What we're looking for is f prime of x, which is d capital F dx. But you see, you got this u in the middle. So what we have to do is this is df du times du dx. Chain rule, right? Now we know what du dx is. That's the 3x squared. Okay? And the df du, we know what that is, because let's change that variable and make this f of u, okay, is equal to the integral. This isn't quite, it doesn't quite feel right, but it's okay. This would be a u up here then, and I'm not comfortable with the pi halves, but let's just not mess with it now. Cosine t dt. Okay, let's just pretend that's not affected by the u. We're just changing the x cubed to a u. Okay? Now, I don't even think that's fair to call that f of u. I think that's still f of x. Okay, I think I'm going to write it that way too. Okay? Now, we just said that df, du, dx, well, df, du is, this would be df, du would then be d by du of this integral. I'm not comfortable with that, but u cosine t dt. Again, this number down here is probably not correct, but it's okay. It's just some number, okay? This we can do. This is going to be cosine u, right? Fundamental theorem of calculus, second fundamental theorem of calculus, okay? But since this thing has to be multiplied by du dx, over here, f prime of x is equal to df du, which is cosine u. Then we multiply that by du dx, which is 3x squared. Okay, and then go back and plug it. This is cosine, but u is x cubed times 3x squared. Okay, which I would write as 3x squared cosine x cubed. The reason is you're only taking the cosine of the x cubed part, and if you have the other part at the end, it thinks it's the same thing. So this is simply cosine, well, they write it cosine x cubed times 3x squared. That's the root of f. Now, there's several things about that I don't find all that and now they're going to turn around and do it the very way I was going to do it to begin with. I don't want to take that much more time in this because we only have about 10 minutes left, a little bit more than that. And in fact, even the net change theorem. Let's just sort of walk through the rest of it. We're almost at the end of the section anyway. 4.4 homework exercises would be, if you need to do some of them, either 5 or 7 or both. They're both at calcchat.com. Any of the odds 9 through 35, they're all at calcchat.com. 19's at calcview.com. Either 37 or 39, they're both at calcchat. 37's at calcview. Any of the odds 41 to 45, they're all at calcchat. 43's at calcview. Any of the odds 47 to 51, they're all at calcchat. 47's at calcview. Any of the odds 53 to 57, they're all at calcchat. 53's at calcview. And either 59 or 61, you choose. There is something there, Buffin's needle experiment. Who in the world is buffing? Okay, that might be a paper topic, though it's probably a little late for one of those. 63 is another one you could do. It's both at Calc Chat and at Calc View. 65 is at Calc Chat but not at Calc View. And 67 is at Calc Chat, not at Calc View. You can do any of the odds 69 to 73. They're all at Calc Chat. 71's at Calc View. And then you can do any of the odds 75 to 79. They're all at Calc Chat. 75's at Calc View. And then you can do any of the odds 81 to 85. Those are more like the one we just did, so you can play with that if you want to. A couple of applied problems. Graphical analysis is 87, water flow 89, velocity 91. You can do any of those you like. Well, actually that is getting into the stuff that we just skipped, so you can stop there if you want to. What I wanted to do, and I hate that we didn't get to do it, is integration by substitution. And I'm afraid y'all are going to need it, so let me introduce it to you at least quickly, okay? Wow, a lot of slides here we didn't get to cover. Sorry that we didn't get to, but the substitution is pretty important, okay? Let me at least introduce it to you. 4.5. This is the last section in the chapter, but it's really a neat thing to do, very useful thing to do. In fact, it's going to be the major part of the next part of integration. The things that are easy, you do. The things that are not easy, here's the first thing you try, substitution. We use a pattern recognition to find an indefinite integral. Use a change of variables to find an indefinite integral. Use a general power rule for integration to find the indefinite integral. Use a change of variables to evaluate a definite integral, and evaluate a definite integral involving an even or an odd function. Let's start with the pattern recognition. We're not going to have too much time for this. I'm going to try to do it as quickly as I can. In this section, we'll study techniques for integrating composite functions. Remember what composite functions are? A function of a function. You know, sine of x squared. Okay? X squared is a function, but the sine is a function of a function. The discussion is split into two parts. The first is pattern recognition, and the next is change of variables. Both techniques involve a U substitution. Now you don't have to use U, it's just everybody's favorite. So that's why they call it that. With pattern recognition, you perform the substitution mentally. With a change of variables, you write the substitution steps. I think I'll jump right to the writing substitution steps. The role of substitution in the integration is comparable to the role of the chain rule in differentiation. You're undoing a chain rule is basically what you're doing. Okay? Now, let's recall for differentiable functions, what if, and this is what we were just doing in a sense, y is equal to f of u. Okay? Now this is a capital F, which you think is the derivative of some other function. And u being some other function, g of x. So the chain rule states if you're doing d by dx of f, you do f prime, which is d by dx of f, then you do evaluated at g, then you do derivative at g. Remember that? That was a chain rule. Okay? When you have a composite function. From the definition of an antiderivative, then it would follow that if you have something as your integrand here that is a derivative of some other function, but then you have the derivative of the function in there too, then you can immediately say this is f of g of x plus c. You always have the plus c for an indefinite integral. Okay? Now, that's pattern recognition, so I'm going to go through this pretty quickly. These results are summarized in the following theorem. Antidifferentiation of a composite function let g of x be let g be a function whose range is an interval I. The range is an interval I. And let f be a function that is continuous on that range of g, which is your domain of f. Continuous on that I. If g is differentiable on its domain, and f is the antiderivative of little f on that domain I, on that range I, then the integral of f of g prime dx would be capital F of g of x plus c. It's exactly what we said before, only different. Letting u equal g of x, this is where the u comes into play. And this is where I think we ought to begin. So let's just skip through this and go back and get to the u part. Okay? I'm going to do this using the u. Okay? Because this is the way we usually go. Okay, here we have an integral of a fairly complicated looking function. Now there's two ways you can do this problem. Okay? One way is you could square this binomial and then multiply 2x by it, and then you're going to have another polynomial that you can integrate just step by step by step. That works, and you could do it. It's a lot of steps to get there, but here's something a little easier. Here's what you look for. Is everybody paying attention? Okay? You look and you see, here is a big function inside the integrand with something else attached. This something else happens to be the derivative of the big function. So at this point, here's what you choose. Let u be the innermost part of the most complicated part of the integrand. The innermost part of the most complicated part of the integrand. So, now this is not how they're suggesting you do the problem, but this is how I'm suggesting. Here's our first statement here.
So pretty much just like u equals x squared.
Say again?
So pretty much just like u equals x squared.
Okay, no. The innermost part of it. Let u equal x squared plus 1. Right? Okay. Now, then, just like we did before, do a du. What is du? Say again? A little up. If that's u, what is du?
Wouldn't D just be the 2?
D is derivative. That's what it means. What's the derivative of u? It's what?
2x.
2x dx. It's in differential form. So now we put the dx on the outside. 2x dx, right?
Yeah.
And looky here. There we have a 2x dx. That's your du, right?
Yeah.
And this is u squared. So your integral becomes the integral of u squared du. I think you can do that, right? Please say yes.
Yeah.
What is it? You said it. Antiderivative of u squared. Say again?
2u.
No, that's the derivative of u
U
squared.
cubed over 3.
U cubed over 3. We just were doing that, remember? Okay. And you need a plus c in there. Okay. So let's do a plus c. But what is u?
U is x squared plus 1.
X squared plus 1 over 3 plus c. Or you could say 1/3 x squared plus 1 plus c. There's your answer. Now, you want to do it that other way? Squaring your x squared plus 1 and then multiplying that by 2x and doing an antiderivative of that polynomial and seeing if it turns out to be this? You could knock yourself out. It will work, by the way. Okay? Now that's not how they do the problem, but guess what? That's the answer. Oh, wait. You let me get by with that. U was that, but then we cubing that. I thought that didn't make sense. Okay. So there you have 1/3 x squared plus 1 cubed plus c. Now, how could you check this? 3 times 1/3 is 1 times x squared plus 1 squared times chain rule 2x. It's exactly what you got here. X squared plus 1 squared times 2x. Yes. So that is indeed what you got there. Okay? Now, I'm going to clear what I wrote. Does anyone need it up a little longer? Okay. So letting g of x, oh boy, they're doing g of x. You could use g of x, or you could use u, okay? U's a lot easier. G of x equal x squared plus 1, g prime of x would then be 2x, f of g of x would be f of x squared plus 1, which would be x squared plus 1 squared. From this, you can recognize that the integram follows the pattern of that, which if that's how you want to look at it, you can. Much easier to just say, let u be blah, blah, blah. Okay. So you carry this all the way through, and sure enough, you get 1/3 x squared plus 1 cubed plus c. Okay. Now, the integrand in this, blah, 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 blah. Okay. Remember, you can always use all of the other rules. Constant multiple, pull the k on the outside and do the integral there. So I don't know why they're mentioning this again. Many integrands contain the essential part, the variable part of g prime of x, but are missing the constant multiple. Multiply it in. It's fine. In such cases, you can multiply and divide by the necessary constant multiple, as shown in example 3, and that's what we're going. Oh wait, they skipped example 2, so let's go back and do example 2. How are we doing? Are we out of time?
It's going to be 10:41 now.
What's that?
It's 10:41.
10:41. So we're through. Sorry. Okay, that was just the taste of substitution. Sorry we didn't get to do a little bit more on that. Okay? Now, folks, I need those earlier papers in. I need the research papers in. I need all that kind of stuff in. Let's see.
Are you going to be on the Birmingham campus at all today?
Not Birmingham.
Okay.
Okay, I'll be there tomorrow from 4 to 6.
Okay.
And Thursday 4 to
I
6.
just have a class this afternoon. I didn't know if you were going to be there.
All right, let me get that to you. That's one.
Here's, you may have to give us your you can wait. That's paper 6:30.
Okay. All right. Code is not here. That's 2. Taylor's not here. Ola's not here. Mike is not here. Tyler is. And you just gave me test 3, right?
Yes.
Yeah, we don't need to.
All right. Now, your last test, test 4.
So
Next
that's the
one.
final.
This is the final. It's not a comprehensive final, it's just the last test, which is the final test. Okay. Pass one over, one back. Okay.
And this is the final.
This is the final.
Okay.
Take home is due back as soon as you can get it to me. Technically Wednesday, but if you need Thursday too, get it to me sometime before the end of the work on Thursday. Now, again, let me say this. Thursday, I'm here on this campus from 7:45 in the morning until 3:30. 3:30, I leave to go to the Birmingham East campus. I'm over there from 4 to 6. Now, if it's not convenient for you to take it to the Birmingham East campus Thursday afternoon, and you want to turn it in and slide it under my door here, when I get in Monday morning, I can grade it then. Okay, but I can't receive anything much later than that. Now let's look at test 4. I'm pretty sure the first 2 problems are from section 4.1. The next 2 are from 4.2. The next 2, I think, are from 4.3. And the next 2, 7 and 8, are from 4.4. Okay? 9 and 10 are actually from the section we were just on, 4.5. We didn't really get to go over them well, so 9 and 10 are bonus. If you can figure out how to do 9 and 10 and get the right answer, you get bonus points. If you get the wrong answer, you don't lose any points. If you leave them blank, you don't lose any points. So 9 and 10 are just bonus.
Do we keep these previous tests?
What's that?
Do we keep these previous tests?
Oh, you do keep them, yeah. Now, the last test that I just gave you, I have to keep this because I like us to keep copies of the final exam for at least 3 years. But I don't know why, but they do. But the rest of them, and if you, any that you turned in today, when you turn in your final, if you want to pick up the ones that you turned in today, you can have them. Because I sure don't want them.
I'll bring the paper by today at 5.
Okay. I'll be here from, like I said, in my office from 4 to 6.
I'll get a.
I mean 2 to 6.
I think Mr. Bryant can tell me where you're at.
What's that?
Mr. Bryant can tell me where you're at.
Mr. Ryan, what?
Bryant can tell me where your office.
Oh yeah, got it. Well, okay, let me show you right now.
I'll show him. We walk out. This
Oh,
one's
okay.
in the hallway.
All right, good deal. All right. Enjoyed having you in class. Please do your student course evaluations.
Yes, sir.
All right, good deal. All right. You need to get me your stuff.
Huh?
You need to get me your stuff. Have you turned in anything yet?
My paper's going to be turned in today, but
Okay.
I've got my other papers.
Okay. And your tests?
That's the other paper.
Oh, okay. Well, you got to turn them in to me. I've been telling you all term long you need to get the stuff in. Okay?
I know, but I don't have the papers.
Pardon me?
I mean, I was just thinking about, I just write everything down, but write all my work down so I can have at least some proof, but
Proof of what?
I mean, I can't give you my papers today.
No, but get them to me as soon as you can. But, I mean, you do this just by every term. You turn in a whole stack of stuff at the end, which is really hard to get graded
Yeah,
at
but
the
I'm
end.
kind of nervous because I'm trying to make sure that it's right by going over it. And then when we learn new stuff, I try to make sure that everything's solid. But then it just keeps.
Well, that's why you should turn it in when I give it out to you. I mean, you should have test 1 in before I give you test 2, so you don't make the same mistakes you did on test 1 on test 2 again. You get to see what you did wrong. So get me the stuff as soon as you can. Just get them to me. Okay?
Sorry. I'm
Okay.
just getting nervous.
Yeah, well, just get them done.